When it is moving in a medium, the propagation is purely an isothermal process. Algebraic sum of displacement of the medium of individual waves is called as superposition of waves. This concept we need to understand two important terms called as nodes and antinodes. There will be no transfer of energy across any section of the medium. Hello everyone, welcome to session 2 of chapter 15 Waves. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in the previous session, we have come across the introductory part of waves where we understood what is the meaning of wave, what are the types and about progressive wave as well. In this session, we are going to learn many more interesting concepts. So let us start with the Newton's formula for speed of sound in gas or speed of sound in air. So we know that sound is an example for longitudinal waves. So what is the speed of sound in air? So a speed of sound can be calculated by a formula that is V is equal to root of modulus of elasticity divided by the density of the medium. Here we have considered the air medium, so rho stands for the density of air. So here, in understanding this concept, let us go through the basic idea behind the formula and what was the imagination of Newton based on the wave propagation. So Newton imagined that the wave propagating in a medium or the speed of sound in air, when it is moving in a medium, the propagation is purely an isothermal process. So he assumed that the wave propagation is basically an isothermal process. As we all know that in isothermal process, the temperature remains constant and it's a very slow process. So he assumes that it's a very slow process so that the system and the surrounding will get enough time to exchange the heat energy, and he will give the formula for speed of sound, that is V is equal to root of P divided by rho. So how to get this? As I said, his imagination was the speed of sound in air. This phenomena is purely isothermal and the equation of state for isothermal process is PV is equal to constant. So differentiating this above term by UV formula, we get P dV plus V into dP is equal to 0. So we can write this formula as P into dV divided by V is equal to minus dP, or we can write this as P is equal to minus dP divided by dV by V, because it is multiplied with P and when it gets transposed it will come to the denominator. Now we can say that it is nothing but change in pressure, and here we can observe that change in volume to original volume. So we can write P is equal to, pressure is nothing but force per unit area, which is nothing but stress. So here the ratio of stress to strain is nothing but the modulus of elasticity. As the force or applied to a system or as the pressure increases, the change in volume decreases, which is nothing but the bulk modulus. So from this expression we can say that this is the expression for bulk modulus, and we can write B is equal to B. Here negative sign says that as the pressure increases, the volume decreases. So from this expression we can write P is equal to B, and the Newton formula is given by V is equal to, here the modulus of elasticity is nothing but the bulk modulus of elasticity square root of B divided by rho, but from this equation V is equal to P and it can be written as V is equal to P divided by rho, where P is nothing but the pressure and rho is nothing but the density of medium. Here we have considered the air medium. So density of air medium, and V is nothing but the velocity of sound. So here P is nothing but the normal pressure at normal temperature of pressure. So the value of V after substituting all the values we get is 280 meter per second, which is not exactly the same as the actual value or the experimental value of speed of sound in air, where the experimental value of speed of sound in air is 330 meter per second. So this theory will get discarded because the value does not match with the actual value. But this formula is modified by Laplace, who corrected the Newton formula by introducing a term called gamma to the above equation, that is V is equal to root of P divided by rho was the Newton formula, and Laplace correct this by introducing a term called gamma, where gamma is nothing but the ratio of specific heats at standard temperature and pressure. The ratio of specific heat is 1.4. So now, how did he introduce this? He assumed that the process is not isothermal as assumed by a Newton, but it is completely adiabatic. Since it is adiabatic, it's a fast process and there will be no time between the system and surrounding to exchange its energies between them, so that it is undergoing a compression, refraction quickly, and hence it is an adiabatic process. So the velocity of sound in air can be calculated by this formula, where gamma is nothing but the ratio of specific heats of gases and rho is the density, P is the pressure. So now, substituting all these values, rho is nothing but the density of air and the value is given by 1.29 kg per meter cube. Substituting all the values, we get the value around 332 meter per second, which is almost nearly equal to 333 meter per second, which is the actual value of the velocity of sound in air, and hence this formula will get approval. But the Newton's formula will be discarded because the value obtained by Newton's formula will not match the experimental value. So this is the Laplace correction to Newton's formula, that is by introducing a term called gamma. So next we have the principle of superposition of waves. What is the meaning of superposition of waves? Superposing means overlapping. So when a medium is distributed simultaneously by any number of waves, the instantaneous displacement of the medium at every point and at every instant is the resultant or the algebraic sum of the displacement of the medium due to individual waves in the absence of others. Which means if a wave is traveling in a medium with a displacement y1 and it is getting superposed with another wave which is traveling, the resultant wave, when they submerge, the amplitude of the resultant wave will be more. That means it is nothing but the addition of the displacement of two waves, which means the algebraic sum of displacement of the medium of individual waves is called as superposition of waves. So next we have reflection of waves. Here in these concepts, we are understanding the properties of waves. What is the meaning of reflection of waves? We all have come across about this phenomena in our daily life. So reflection of wave is nothing but when mechanical wave reaches a rigid boundary, it gets reflected. So what is the example that we can give to understand this phenomena? That is nothing but the echo. So there is a change in path of the wave when it is retracing back, when it is reflecting back, the path of the wave will change and it is turned back into the same medium, obeying the law of reflection. So as I said, the best example to understand this reflection of wave is an echo. So echo is nothing but the sound heard after reflection at a distant rigid boundaries such as walls, buildings or cliffs. So when we shout at once and we will be able to hear it many times, that's an echo. That is because of the reflection of waves. And reverberation, that is nothing but the persistence of sound after the source has stopped producing sound. That is a reverberation. Again, it's a phenomenon. It's an example for the phenomenon of reflection of waves. So next important concept is standing wave. What is the meaning of standing wave? So when two progressive waves of same wavelength and same amplitude travel with the same speed through a medium in opposite direction, they superpose upon each other. So when two waves traveling, one wave is traveling in this direction, the other wave is traveling in the different direction, opposite direction, they overlap on each other, they superpose on each other, and the resultant wave pattern appears to be steady or stationary. So when they are traveling in opposite direction with same speed, same wavelength and same frequency, they looks like a steady, a stationary, and hence the name stationary wave, or also it is called as standing wave. So in this concept, we need to understand two important terms called as nodes and antinodes. What is the meaning of node? Node is nothing but the position at which the amplitude of a particle is minimum. So here in this picture, the red dots represents nodes. where we can observe the amplitude is 0. What is amplitude? Maximum displacement. They are at their mean position and hence no displacement, so the amplitude is 0. So antinodes are nothing but the position at which the amplitude of the vibrating particle is maximum. So here these are the positions of antinodes where the displacement of a particle or the amplitude of the particle is maximum, we'll call it as antinode. So if the one wave is traveling in this direction, the other wave is traveling in the opposite direction, these are the points where nodes forms, and here with maximum amplitude we'll call it as antinodes. And next important term to understand is loop. What is the meaning of loop? A waveform between two consecutive nodes. You can observe here, this is one node, this is the another node. The waveform between two consecutive nodes, it will give us the formation like this, and it is called as loop. It is also called as a loop or a segment. So now this is about the standing wave. Let us now study about the characteristics of standing wave. In the previous session, we have learnt about the characteristics of progressive wave. So let us now study about the characteristics of standing wave, which is again important to differentiate between the progressive wave and the standing wave, or it is also called as the stationary wave. Both are same. So the first characteristic is the waveform doesn't advance through medium. It seems stationary when two waves travels in opposite direction with same wavelength and frequency, and hence the waveform doesn't advance through medium, and hence there will be no flow of energy. There will be no transfer of energy across any section of the medium. In progressive wave, no particles will be at rest position. They'll be moving continuously, and hence the transfer of energy will take place. But it is converse in case of standing wave. There will be no transfer of energy in case of standing wave or stationary wave. The amplitude of vibration from point to point varies because we know at nodes the amplitude is minimum. At antinodes the amplitude is maximum, whereas in case of progressive wave it is not like that. The amplitude of all the particles will be same. So it gradually increases from 0 at nodes to maximum at antinodes. That is what we have learned till now in the study of stationary waves. And particles lying between any two nodes moves in the same direction at the same time. So they have same phase. No particle in progressive wave has same phase, but in case of stationary waves or the standing waves, the particles may have the same phase because the particles lie between two nodes move in the same direction. Not only in the same direction, but also they move at the same time, and hence they can have the same phase. So these are the characteristics and also the differences between the progressive and stationary waves. So in stationary waves, we need to understand few important terms. The first one is fundamental mode. As the name says, fundamental means the basic. So fundamental mode is nothing but the mode of vibration with lowest frequency, the fundamental frequency, and the corresponding frequency is known as fundamental frequency. The mode of vibration with lowest frequency is called as fundamental frequency. Then what is the meaning of overtones? So overtones are nothing but the mode of vibration which produces the notes of higher frequency. The notes of higher frequency are called as overtones, and harmonics are nothing but if the frequencies of overtones are integral multiple of fundamental frequency, they are called as harmonics. So basically the least or the lowest mode of vibration or the lowest frequency is called as fundamental frequency, and the vibration which produces the notes of higher frequency called as overtones, and the frequency of overtones which are the integral multiple of fundamental frequency are called as harmonics. So next we are going to understand the modes of vibration of air column in a closed pipe. So to study this modes of vibration in air column, we will consider two types of pipe. One is the closed pipe, the other one is the open pipe. What's the meaning of closed pipe? Closed pipe, you can observe here, one of the end of the pipe is closed and the other end will be open. That is a closed pipe. And open pipe means both the ends of the pipe will be open, no end will be closed. So this is the basic difference between closed and open pipe. Now we are going to understand what is the mode of vibration of air column in a closed pipe. Now we have considered three modes of vibrations here. The first one is the fundamental mode, and here there is a condition is at closed end always there will be a formation of node, and at the open end there will be formation of antinode. You can observe here the amplitude is maximum, and here is the formation of antinode, and this is the node where it is formed at the closed end. So here the length of this pipe is considered as L. As we all know that if this is a complete wave, this is the loop. Loop is nothing but the distance between two nodes. A complete wave distance is called as wavelength. So the half of this, here we are studying about the stationary wave, the half of this forms loop, and the distance between this will be half of lambda, that is lambda by 2. Now the half of this loop gives us this structure, and this will be lambda by 4. So now we can observe here it is the half of one complete loop. One complete loop means this one, but we have only the half of loop. So loop means it is given by lambda by 2. So half of this is nothing but lambda by 4. So the length of this will be lambda by 4, and since it is the first mode of vibration, I'll consider it as lambda 1 divided by 4. Here the length of this pipe will be, you can observe here I have lambda by 4 and here we have lambda by 2. So lambda by 2 plus lambda by 4 gives us 3 lambda 2, since it is second mode of vibration, divided by 4. Similarly here we have lambda by 2, lambda by 2 and lambda by 4, and the length will be 5 lambda 3 divided by 4. So this is the length of pipe. So now we have to write the modes of vibration of this air column for this closed pipe structure. So let us now take the length of the first mode, that is L is equal to lambda by 4, or we can write it as lambda is equal to 4L. We have the expression called V is equal to F lambda, and from this we can write F is equal to V by lambda. Here the fundamental frequency F equal to V divided by lambda is nothing but the 4L. So it is V divided by 4L is the fundamental frequency. Similarly, we have here L is equal to 3 lambda 2 by 4, and we can write it as 4L is equal to 3 lambda 2, or lambda 2 is equal to 4L divided by 3. So now we have V is equal to F lambda relation, F is equal to V by lambda, or V divided by lambda is nothing but 4L divided by 3, or we can write it as 3V divided by 4L. Here we can say that V by 4L is nothing but F1. So we can write here F2, that is second mode of vibration. The frequency for second mode F2 is equal to 3, as it is I am writing V by 4L is nothing but F1. So it is 3 into F1. So here we can observe the integral multiple of fundamental frequency, and it is nothing but the harmonic. So it's a first harmonic. So next third mode we have L is equal to 5 lambda 3 by 4, and we can write it as lambda 3 is equal to 4L divided by 5, and we have relation V is equal to F lambda. F is nothing but the third, for the third mode of vibration we are writing, so it is F3 is equal to V by lambda. It is nothing but V divided by lambda 3, that is given by 4L divided by 5, or I can write it as F3 is equal to 5V divided by 4L. But what is V divided by 4L? It is F1. So I can write it as F3 is equal to 5 into F1. It is again the integral multiple of fundamental frequencies. So from these three concepts we can write F1 is to F2 is to F3 is equal to 1 is to 3 is to 5, which means in the closed mode of vibration we can observe the odd harmonics presence. It means in closed pipe we can only observe the odd harmonics, that is 1 is to 3 is to 5. So this is the conclusion for mode of vibration of air column in a closed pipe. So next let us now study about the modes of vibration of air column in open pipe. I told you about open pipe where both the ends of the pipe is open. So we know the condition that at open end the antinodes will form. There will be no formation of node at open end. Since it is open at all the ends, both the ends, so in all the modes of vibration we can observe the antinodes at the ends. So here you can observe we have lambda by 4 plus lambda by 4. So lambda by 4 plus lambda by 4 gives us lambda by 2 is the length of first mode of vibration. Since it is first mode of vibration, I can write it as lambda 1 divided by 2. But here you can observe lambda by 4 plus lambda by 4. That's lambda by 2 plus lambda by 2. So lambda by 2 plus lambda by 2 is nothing but lambda, which means half plus half is equal to 1. So in the second mode of vibration, I'll take it as lambda by 2. So in third mode of vibration, you can observe lambda by 2 plus lambda by 2, and here we have lambda by 4, lambda by 4. So if you add these lambda by 4 and lambda by 4, we'll get lambda by 2 only. So there are totally 3 lambda by 2 we have in third mode of vibration. Since it is third mode, I'll take it as lambda 3. So now the length of this pipe for third mode of vibration is 3 lambda 3 by 2, and for second mode it is L is given by lambda 2, and for first mode it is lambda 1 divided by 2. So let us now take first mode of vibration. So first mode L is equal to lambda 1 by 2. So from this we can write lambda 1 is equal to 2L. We have a relation V is equal to F lambda, where F can be written as V by lambda. So F is equal to V divided by lambda is 2L is the frequency of first mode of vibration. Similarly for second mode. For second mode, length is nothing but lambda 2. Now we have V is equal to F lambda and F is equal to V by lambda. So F is equal to V divided by lambda 2, or we can write it as F is equal to V divided by lambda 2 is nothing but L. Since we have to represent this in terms of integral mode, we can write it as F is equal to multiplying 2 on both the numerator and denominator 2V divided by 2L. But what is V divided by 2L? It is F1. So here we can write F2 is equal to 2 into F1. So that it can be represented in integral modes of vibration. So next we'll take third mode of vibration, where the length is given by 3 lambda 3 divided by 2, or lambda 3 is equal to 2L divided by 3. V is equal to F lambda, F is equal to V by lambda. So F is equal to V divided by lambda is 2L divided by 3, or it can be written as 3 into V by 2L. So V by 2L is nothing but F1. So here F3 is equal to 3 into F1. So in case of open pipe, the modes of vibration can be written as F1 is to F2 is to F3 is equal to 1 is to 2 is to 3, which means in open pipe, the modes of vibration will be both the integral multiple. It is not only the odd harmonics present, the integral harmonics will be present in case of the open pipe, and this is the conclusion for modes of vibration of air column in open pipe. So next let's move on to an important concept called beats. So what is the meaning of beats? So it is nothing but the waxing and waning, or the periodic rise and fall in the intensity of sound due to superposition of two sound waves of slightly different frequencies. So when two different frequencies sound waves superpose on each other, there will be a production of some noise. That is due to the periodic rise or fall of intensity of sound, and it is called as beats. And in the formation of beats, we have to be careful that we need to understand that the two waves are traveling in same direction. When two waves of different frequencies, slightly different frequencies traveling in the same direction, due to their superposition, the periodic rise or fall in the intensity is called as beats. Say for example, here one wave is traveling in one direction, the other one is traveling in the same direction with different frequencies. You can observe the different frequencies, where you can observe here the waning is there, and here the maximum intensity, here it is negative intensity. When they both superpose on each other, we can observe the rise or fall in the intensities in the resultant wave. So the the amplitude will be maximum when crest of one wave falls on the crest of the other wave. The amplitude of the resultant wave will be minimum when crest of one wave will fall on the trough of the another wave. Because of the slightly difference in frequencies of two waves which are traveling in the same direction, the waxing or wannings will produce, and this is the resultant of the superposition of two waves and the name called as beats. So beats are the very important concept, that is, so the beat frequency is given by FB, which is nothing but the difference in frequencies of two waves, where F1 and F2 are the frequencies of two waves respectively. When there is slight difference in the frequencies of two waves, there will be a formation of beats, and the frequency of beats can be calculated by the formula F1 difference F2. By taking the difference of two frequencies, we can find the frequency of beats. So this is the very important formula to find the beat frequency. So let's move on to the next topic and the last topic of this chapter called Doppler Effect. So Doppler Effect gives us an idea to understand the apparent frequency. So this phenomena also we have all come across in our daily life. So Doppler effect says that the change in the pitch or the frequency of the sound heard by observer due to the relative motion between the source and the observer. When there is a relative motion between the source and observer, the apparent frequency heard by observer is explained by a Doppler effect. Say for example, when we are in the stationary platform, the train approaches us, so it will blow its whistle in the same frequency, but when it is coming towards us, we will feel like the sound intensity is more, and that is called as apparent frequency. And when train recedes us, when train passes away from us, the sound, the whistle of train will be heard slower, or the pitch or the frequency will be less than it. Pitch or the frequency what we hear as an observer will be slightly less, and that is called as apparent frequency. In various conditions, the apparent frequency can be explained with the help of Doppler effect, and this is very important concept. In final examination, we will get problems based on Doppler effect. So basically, the apparent change in a frequency or pitch of sounds heard by the observer due to the relative motion. Relative motion means the motion of source or an observer with respect to each other is called as Doppler effect. So based on the conditions, we have different formula in Doppler effect. When the observer is stationary and the source is moving towards him and it is moving away from him. Similarly, when source is at rest position, observer is moving towards stationary source, moving away from stationary source. Based on all these conditions, there are few formulae on which the problem will be asked for the examination. So we suggest all our students to work on it. Doppler effect is very important for 5 marks. So in this session, we have studied about the properties of progressive wave, stationary wave, differences between stationary and progressive wave, modes of vibration in closed and open pipe, and many more interesting concepts. So this is the end of your syllabus, children. All the best for your examination. Do well. Thank you.